Well, that's what we've been doing. We've been doing it with technology, though, because fluency can be achieved without technology. I bet there's not a person in this room that learned their math facts with technology or computer. Am I right? There's a reason for that. Anyway, but we all learned our facts, all right? Everyone in this room learned their math. I happen to have a mother who sat me down every night with flashcards and worked with me until I knew my facts. She beat them into me, all right? Thank God she did, because the problem is, we don't have mothers that are doing that today. That's not saying anything bad about mothers. They got a lot going on, but we're not seeing kids learning their facts outside of the classroom. And what we're doing in the classroom doesn't seem to work in most cases for these kids. The other thing is, for a long time, we assumed that computerized drill and practice would take care of the problem. Actually, back in the 80s and 90s, there were a lot of articles talking about fluency will no longer be a problem because of computers, all right? It's not true. We actually did a study in Nashville that we found no evidence that the use of drill and practice on a computer made any difference at all. Actually, what we did is we took a group of students for an entire semester, gave them 10 minutes of practice every day on a game called Alien Addition. Some of you might remember that program. Anyway, it randomly presented addition facts to kids. They loved the game. We had to rip them off the computer so the next kid could go on. They loved playing the game, all right? But in the end, we had kids that had done over 7,000 trials of individual facts, all right? We didn't find one student, not one student, that gave up counting on their fingers in favor of storing it and retrieving it, okay? All we did was make the fastest finger counters in all of Nashville, Tennessee. Those kids were so fast to count. But we couldn't find any evidence. Now, luckily, we had done a chronometric analysis ahead of time. And remember that chronometric analysis, that some facts fall off that regression line, often it's doubles, sometimes doubles plus or minus 1. What we found is for those facts that were not on the regression line, the response latencies dropped down to around 200 milliseconds, very, very fast. And that was the insight that we needed, because we then understood that randomized practice simply speeds up the retrieval of facts already stored, but in no case do we find kids giving up counting on their fingers in favor of storing it. In other words, and there's a reason for that, because we were randomly presenting them and we were giving them too much information, so by the time they saw the fourth or fifth problem, they'd forgotten what the first problem was they saw. They can't hold that much information in working memory. We've got to reduce that cognitive load. And that's what we did. We created a model called the FASTT model to do that. And the FASTT model has 6 steps: assessment, small instruction set, controlled response time, corrective feedback, expanding recall, and practice only learned information. We don't let kids practice what we know they've stored. Okay? Now, let's look at this a little more carefully. So there are three parts to this: assessment, adaptive instruction, independent practice. Under assessment, first of all, we look at concept assessment. The kids have a conceptual understanding of the operation. If the answer is no, then you got a bigger problem than fluency. Okay, you need to go back and build that conceptual understanding. The worst thing to do is to try to build fluency without that conceptual understanding. Then we did a keyboarding assessment. We simply want to know how fast are the kids at typing in the numbers. And that's a simple thing. All you do is you put a number on the screen, like 14, and see how long it takes them to type that number. All right, that's their keyboarding time. Then you give them a fact assessment. You put up 7 plus 7. The answer is 14. How long did it take them to type in 14? And then you subtract out the keyboarding time from their total time, and what you have is the processing time, okay? And when we do that, it simply looks like this. You put up a problem, whoops, and you measure the total time, subtract out, in this case, it would be for 15, and what's left over is their keyboard, or their processing time. If it's less than 0.8 seconds, then we know it's not fluent, or if it's wrong, okay? If it's correct and under 0.8 seconds, we put it over there and let them practice it, because what we'll do is simply speed that up. Now, what about instruction for those facts that aren't fluent? Well, we build on existing facts. If you remember that matrix I showed you, we start with the lowest fact that those kids have not stored. We build on where they are. We use a small instruction set, and I mean very small. kids never get more than 3 new facts at a time, and usually it's 2, and the 2 are usually a fact set and the reversal. What we're trying to do is lower that cognitive load as much as we can for those kids, all right? Then we require them to recall that fact set that they're working on from working memory. The way we do that is we ask them to type in that number line. If they can do that, if they can type in that number line in the answer, that tells me it's at least in working memory. It hasn't fallen out, okay? It's got to be in working memory. And then what we do is we start rehearsing it in working memory and we provide feedback. Now, it might look like this. So they would see, today you're working on 7 plus 3 equals 10 and 3 plus 7 equals 10. We ask them to remember that. All right? We never give them the fact without the answer because we want them to pair these. And the next screen they see is this. All right? Now, what they have to do is hold that fact set that they're working on long enough in working memory to type it in. If they do that, that tells me at least they're holding it in working memory. All right? And when they're successful, then we immediately start going in and providing them that guided practice on that fact set. Now, we look also in the guided practice, we use something called controlled response time. We only give them 1.25 seconds over their expected keyboarding time, all right? And the reason being is that if I give them more than 1.25 seconds, what are they going to do? They're going to, yeah, exactly. They're going to go 7, 8, 9, 10, all right? And we don't want them to do that. We want them to give that up. So we only give them 1.25 seconds. And if they don't do it under 1.25 seconds, we stop them and say, oh, you're out of time. 7 plus 3 equals 10. And then we give them the problem again, and they have to type it in. We're trying to build that paired association. And we use something called spaced presentation of new information using expanding recall. It's a big word for just the way we present. Now, back in 1885, Ebbinghaus did work in moving information from working to long-term memory. And he found that the one way that you can do is what we call masked trials. And that is, you see 7 plus 3, then you wait a second, you see 7 plus 3 or 3 plus 7, wait a second, 7. You just keep going over the same thing over and over again. What he found is that wasn't as efficient as if you put more time, about 10 seconds between those trials. So you see 7 plus 3, 7 plus 3 or 3 plus 7, 7 plus 3, so you wait longer time. Now the problem is that's a more efficient way, or was a more efficient way, for over 100 years, we thought, to get information in long-term memory. Then came along another study that said, no, that's not really true. That there's something called expanding rehearsal that is more efficient than distributed rehearsal. So you wait, you present it, 7 plus 3, wait a second, 7 plus 3, wait 2 seconds, 7 plus 3, wait 4 seconds, 7 plus 3, wait 8 seconds. You keep expanding that amount of time. And it makes perfect sense because here you're rehearsing this in working memory, all right? And then you keep going longer and longer periods. Eventually, you have to move it to long-term storage, all right? And the problem with this is that, you know, with any kid, but certainly with struggling students, what do you do for those long periods of time in between? You sit there and look at them? I mean, it's not a very practical thing to do.